Okay, welcome to our discussion about elastic collisions. So an elastic collision is a collision where the kinetic energy of the system is the same before and after the collision. And that's what's special about elastic collisions. Of course, in a collision where any kind of collision where there's no external forces, we also have momentum conserved. So we have two things conserved in an elastic collision. We have the momentum is conserved, and we have the kinetic energy is conserved. Alright, so we have two equations that you can see here. And these two equations are sufficient enough to figure out the velocities of two objects after the collision, as shown in example 8. You have object A here and object B both going towards each other, and what you're asked to do is to figure out the final velocity of both of these. And you could use that, but as you may notice in the kinetic energy formula, there's a v final squared here and another v final squared here, and that can be a little bit harder to work with. So there is a nice, neat derivation of what we call relative velocity for elastic collision. And this is not on the formula sheet, but I'm going to allow you to use that on a test or a quiz or whatnot. This is only true for elastic collisions. Okay? Now you might be wondering, where did this equation come from? So I'll just take a quick little aside here and show you that. So what I've done is I've written down the kinetic energy formula here, and I'm going to do some rearranging of this so that the halves, first of all, we can cancel all of that. And what we'll do is we'll put the M1 and M2 combined on each side. So what I'm going to do is I'm going to put M2 over here, and I have M2 V2 initial squared, and bring over this M2 term, so M2 V2 final squared, and that's going to be equal to M1 V1 final squared minus M1 V1 initial squared. And let's collect like terms here, M2 and write V2 initial squared minus V2 final squared, and that's equal to M1 brackets V1 final squared minus V1 initial squared. And now what I'll do is I'll factor out here. I'll rewrite this as V2 initial minus V2 final brackets V2 initial plus V2 final, and that's equal to a similar expression on the right side, V1 final minus V1 initial and V1 final plus V1 initial. So you hopefully should see that this expression is really the same as this one below it. And we're doing that because let's now turn our attention back to our momentum. Momentum initially equals momentum finally, and so we get the following equation. And we get M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And once again, what I'll do is I will collect like terms similar to what I did over there. I'll write M2 V2 initial minus M2 V2 final equals M1 V1 final minus M1 V1 initial, and pull out an M2, and I get V2 initial minus V2 final equals M1 V1 final minus V1 initial. And so what you should see is two equations that have some similar parts. Hopefully you'll recognize that this part here is the same as that part, and this part here is the same as that part here. And so what I'm going to do is I'm going to divide these two equations by each other. So I'm going to take number 1 equation and number 2, and I'm just going to simply put them on top of each other, divide out. And so I get M2 V2 initial minus V2 final, V2 initial plus V2 final, and that's going to be divided by M2 V2 initial minus V2 final equals M1 V1 final minus V1 initial, V1 final plus V1 initial, and all of that divided by M1 V1 final minus V1 initial. And you should see that this will cancel out with this piece, and this will cancel out with this piece, and you'll get V2 initial plus V2 final equals V1 final plus V1 initial. So if we were to rearrange this once again so that we get V1 initial minus V2 initial, and that will be equal to V2 final minus V1 final. Or you could look at this as V1 initial minus V2 initial equals the negative of V1 final minus V2 final. And these are what we call relative velocities. This is a relative velocity, and this is a relative velocity. So you can think of this speed, this difference between V1 initial and V2 initial really being the speed of approach. So like kind of like a closing speed coming towards each other, how fast this is relative to that. And then the speed as they leave, this is the speed of separation after the collision. And so what we see is that the speed of separation equals the speed of approach, but there's a negative sign in here. And so this equation is very helpful and makes the problems that we were solving with the elastic collisions easier than using the kinetic energy formula. So going back to our elastic collisions, we had this equation over here for conservation of momentum. We had this equation here for conservation of kinetic energy. But now you have a third equation that makes things a lot easier to solve. This is an equation which we call a relative velocity. So the relative velocity of the two objects approaching each other is equal to the negative of the relative velocity of the objects as they recede from one another after the collision. So this is only true for elastic collisions. So there's the same equation written down here. So now you're ready to tackle on example 8.